pioneering hydrogen storage systems for zero-emission aviation. In an era when reducing carbon emissions is not just a goal, but an imperative, researchers at the FAMU-FSU College of Engineering are rewriting the rules of sustainable flight. Their groundbreaking work in developing a liquid hydrogen storage and delivery system promises to elevate zero-emission aviation from visionary concept to near-term commercial reality, even as early as 2035. Bridging the hydrogen divide. Hydrogen's potential as an aviation fuel is undisputed. Its energy density far surpasses conventional jet fuel, and it burns without producing carbon dioxide. However, its practical adoption is hampered by formidable engineering challenges. Storing hydrogen safely requires cooling it to a staggering -487.4 degrees and 253 degrees, and traditional techniques rely on heavy, separate systems to manage fuel storage and thermal regulation. This dichotomy has long been the Achilles heel for hydrogen's role in aviation. The FAMU-FSU team has taken a holistic approach by designing an integrated system that uses hydrogen not only as fuel, but as a built-in cooling agent. This synergy is a paradigm shift, eliminating the need for bulky additional equipment while solving multiple technical hurdles simultaneously. The heart of the innovation, technical advances unpacked, a leap in gravimetric efficiency. One of the most impressive breakthroughs achieved is the development of a system with a gravimetric index of 0.62. In simple terms, 62% of the total weight of the storage system is usable hydrogen, not the heavy, cumbersome structure typical of conventional designs. This dramatic improvement means that every kilogram saved on structure is another kilogram available to power the future of flight. Pump-free, pressure-regulated delivery. Mechanical pumps, indispensable in many fuel systems, become liabilities under cryogenic conditions. They add both weight and potential failure points. Addressing this, the FAMU-FSU engineers have devised a pump-free delivery mechanism. By regulating tank pressure through dynamically controlled feedback loops, the system adjusts fuel flow in real time. High-pressure injections boost flow when needed, while venting excess vapor fine-tunes the balance. This elegant solution minimizes moving parts, enhances reliability, and optimizes the delivery of hydrogen under the severe conditions of flight. Integrated thermal management, dual-purpose design. Perhaps the most innovative aspect of the system lies in its use of hydrogen for thermal management. By channeling the ultra-cold liquid hydrogen through a series of strategically placed heat exchangers, the system performs a dual function. First, it cools critical high-performance components, such as superconducting generators, motors, and power electronics. In doing so, it extracts waste heat and, simultaneously, preheats the hydrogen to optimal operating temperatures for fuel cells and turbines. This staged thermal integration not only streamlines system architecture, but also directly contributes to overall energy efficiency, setting the stage for truly sustainable aviation. Meeting the demands of modern flight. Simulation studies underscore the system's robust performance. With hydrogen delivery rates reaching 0.25 kilograms per second, it can supply up to 16.2 megawatts of electrical power, precisely what is required during the high-demand phases of takeoff or emergency maneuvers. The focus on system-level optimization, including the precise management of vent pressures and heat exchanger dimensions, ensures that the design is primed for commercial aviation use. Toward commercialization and beyond. While detailed simulations mark a significant step forward, the journey from concept to widespread adoption continues. The next phase involves building a prototype system for experimental validation, a critical milestone under NASA's Integrated Zero-Emission Aviation program. This initiative, which brings together leading institutions nationwide, is instrumental in driving research that translates into operational zero-emission aircraft. Beyond aviation, the principles underlying this hydrogen storage system have far-reaching implications. The integrated approach to fuel storage and thermal management could transform storage solutions in other high-demand sectors, laying the groundwork for a broader hydrogen economy. Redefining the future of flight. The work at FAMU-FSU sets a new industry benchmark. It challenges long-held assumptions about the limits of hydrogen as an aviation fuel and provides a realistic pathway for integrating hydrogen's inherent advantages with the demanding thermal and power control requirements of modern aircraft. For industry leaders and policymakers alike, this research is not only a signal that zero-emission aviation is achievable, it's a blueprint for how to get there. As the aviation industry inches closer to a decarbonized future, embracing innovations like these will be critical. The fusion of fuel and cooling in a single optimized system may well mark the turning point for sustainable flight, impacting everything from commercial travel to broader transportation networks. You've been listening to Sustainability Soundbites from E+E Leader. For more information on sponsorship opportunities, reach out to our team today.